This lesson involves a special type of reaction that aldehydes and ketones undergo called an aldol reaction, and it involves a special type of intermediate called an enolate, and you can see this comes from these first 4 sections of chapter 20 in your book. The hard copy of this document I'm looking at here, you can download your own copy if you want to follow along as I talk about this. Before we get to that chapter 20 stuff though, back in chapter 9 we were talking about alkynes, and one of the important things that you can do with an alkyne is remove a hydrogen that's attached to a carbon where that triple bond is. Now it takes a very strong base to do this. We're talking about this thing, NH2, called amide. That is a base that is strong enough to take away this hydrogen, creates a carbon with a negative charge, a carbanion, and what's useful about that is that you can then treat this like any nucleophile and do some more chemistry with it. There's a pair of electrons here associated with that negative charge, and if we then, for example, mix this with, say, ethyl chloride, we can do this type of substitution reaction where our chloride is our leaving atom, and the outcome of that turns what starts off as a 2-carbon chain becomes a 4-carbon chain, and you can build that chain of essentially any length you like depending on how many carbons are in your alkyl halide and how many are in the alkyne. The limitation of this reaction is that you have to do this in liquid ammonia. You can't do it at room temperature. You can't do it in a simple solvent like water or alcohol, and in fact the fate of the amide ion, once the hydrogen is removed, if you're using that particular base, you make ammonia. You wouldn't actually make a free hydrogen ion. You would just essentially transfer that hydrogen from the alkyne to the NH2. So that's still a useful reaction. It's just sometimes not practical to make work. What's nice about the reactions we are going to talk about in this chapter, the aldol reactions and the enolates, is that we can use much milder conditions. We're identifying here these alpha hydrogens. They're hydrogens on a carbon that's next door to a carbonyl, like you have in this 2-carbon aldehyde here. It's much easier to remove one of those alpha hydrogens. We can use bases like hydroxide or methoxide. We can do this at room temperature, and the key to being able to do that is that these numbers, these pKa numbers, are so different. pKa is a scale of how strong an acid is, how easily one can remove hydrogens from an organic compound like these. And it's a logarithmic scale, so the difference in these numbers, 26 and 17, is 9. So that actually means that this aldehyde down here is 10 to the 9th times as acidic as the alkyne above, or it's 1 billion times easier to remove that hydrogen. And so we're showing the similar type of reaction here in which a hydrogen is being removed. It's just a lot easier to do it with that type of hydrogen compared to an alkyne. Scroll down here a little bit, you can see this in action. Here I'm showing plain old hydroxide as our base, and this could be done perhaps in water or in alcohol, and so the hydroxide gets that extra hydrogen to turn itself into water, but now we've created this thing we call an enolate, carbanion that is very useful for subsequent reactions. And here's why it's called an enolate. Put in the 2 electrons that would be present on that carbon with a negative charge. I can draw this other resonance form by reassigning those to make that a double bond. At the same time, the double bond to oxygen becomes a single bond, and so we relocate some electrons. And what we have over here on the right side, it's the negative ion of something that we would call an enol. If it were a complete enol, that oxygen would have an H on it. So you can see it's alkene and alcohol, so enol makes that combination. And when we don't have that hydrogen on that oxygen, we call it an enolate. So that ATE usually refers to a negatively charged something in chemistry, oftentimes where there's oxygens involved. But this resonance form on the left is really how these enolates react, because just like the alkynes above, it's that negative charge on a carbon that's really the key. because we can use that to make a new carbon-carbon bond if we react this enolate with something else. And as it says here, we do think of that left-hand structure as really the active one. That's really going to tell us about what the fate of this enolate is if it reacts with something else, and we'll take a look at that in the next little video.